Hey there, everybody. Welcome back. This is 14.7 in Calculus 3. We are looking at the equivalent of the U sub in multidimensionals. We get the Jacobian. We showed the theory behind it in the last one. Let's just look at some examples here. Let's say we're going from x, y to r and theta. A good old polar. So we know how polar turned out. dx dy turned into r dr d theta. Does the Jacobian yield that? So x equals r cosine theta, y equals r sine theta. We do our little Jacobian matrix. We got derivative of x with respect to r and theta across the top, derivative of y with respect to r and theta across the bottom. So cosine theta, sine theta, and then negative r sine theta, r cosine theta. We can see that we are going to have r cosine squared minus negative r sine squared. You'll see that just gives us the absolute value of r. But since radius is greater than 0, it's just r. So that is our Jacobian. dAxy goes to the Jacobian under r and theta, dr d theta. And the Jacobian gave us our r. Okay, that's just one we know already. So r dr d theta. Let's look at the example we did a little bit ago, where x equaled u squared minus v squared, y equals 2u. We're going to integrate it. We're going to start with this integral, which was the x and y, and that's crappy. Okay. I don't want to integrate this. Well, it's not crappy, but the limits are less fun on this. I'm gonna have some curves. If I could make it easier. It's not too bad. Let's integrate with respect to y, and we're gonna switch over to uv rather than just doing it as is. Okay. So when we switch over to uv, we are in a rectangle from 0 to 1 on both dimensions. That was our uv. And that was our mapping. X equals u squared minus v squared, y equals 2uv. When we do the Jacobian, the derivative of x with respect to u and v across the top, the derivative of y with respect to u and v across the bottom times du dv. I get xu yv minus xv yu. If I plug those in, derivative of x with respect to u is 2u. Derivative of y with respect to v is 2u also, so we're going to get 4u squared there. And then xv yu is negative 2v and 2v. So we get a negative 4v squared, but we are subtracting, so it becomes positive. So I have 4u squared plus 4v squared du dv. That's our Jacobian right there. J of u and v. So our y, we're doing the integral of y. Y was 2uv. So that's my y. This is my Jacobian, and this is our new coordinate system, du and dv. We're just going from 0 to 1 on both of them. Simple little limits of integration. You can go ahead and pause the video if you want to chug through it, but you should get 2. Okay. So this was an easy to solve problem. We had a suitable change of variables. The original problem wasn't too bad. It was pretty easy once we switched. If f of x, y is difficult to integrate, the form of f might suggest a suitable transformation, like polar or something of that nature. If the limits are what's difficult, like it's a screwed up looking shape, choosing a transform where it makes the limits nice might be the way to go. So a little example of this. So if it's the crappy region in u and v, or x and y, like these are crappy to integrate, try to find something that makes the limits go to something nice. And then if the actual function we're integrating is shitty, like maybe square root of x minus y or x plus y, This one's not too bad, but we could do a transform for it. Here I would do U for the top, V for the denominator. And that makes our function now nice and neat. These are easy to integrate. Okay, this is easy to integrate too, and there we go. That's it for this video. We got more examples in just a second. Peace.